The atmosphere is essentially a collection of gases that makes the Earth habitable. The atmosphere is made up of 5 different zones or layers. The first layer is called the troposphere. The troposphere starts at ground level and extends upward about 10 kilometers above sea level. The second layer is called the stratosphere. The stratosphere extends from the top of the troposphere to about 50 kilometers above the ground. The ozone layer, the basis of the experiment explained in this video, is found in this layer. The third layer is the mesosphere. The mesosphere extends to a height of about 85 kilometers above our planet. The fourth layer of the atmosphere is called the thermosphere. The thermosphere can reach anywhere between 500 and 1,000 kilometers above the ground. The fifth and final layer of the atmosphere is called the exosphere. The exosphere is a very thin layer above the thermosphere. There is no clear boundary of where this layer ends, and sometimes it is not even considered to be an actual layer of our atmosphere.
The ozone is a layer within the stratosphere. Ozone is a trace gas in the atmosphere. There are only 3 molecules of ozone for every 10 molecules of air. Ozone's job is to absorb radiation hitting the Earth from the sun and converts it to heat. Radiation from the sun is necessary to live, but too much can be damaging. The ozone layers act as a shield for life on Earth. Ultraviolet radiation, or UV light, can penetrate organisms' protective layers, like skin, and damage DNA molecules in plants and animals. The ozone is getting thinner due to the effects of chemicals called chlorofluorocarbons, which contain the elements carbon, chlorine, and fluorine. They are everywhere, but mainly in plastic products and refrigerants. While they do not usually poison living things, they eat away at the ozone layer once they get blown into the stratosphere.
The Montreal Protocol on substances that deplete the ozone layer was designed to reduce the production and consumption of ozone-depleting substances. There are 11 different categories of controlled substances that are known to deplete the ozone layer listed in this protocol. Emergence of healing in the Antarctic ozone layer was an experiment completed by Susan Solomon and colleagues at MIT. The purpose of this study was to explore the changes and patterns of ozone depletion as a result of CFCs and healing since the implementation of the Montreal Protocol. In this article, 3 models were used to simulate why the ozone has changed since the year 2000. One accounted for changes in temperature and winds, one considered only background sources of stratospheric sulfur, and one was a chemistry-based solution where meteorological conditions were kept constant.
Ozone recovery occurs through 3 distinct steps. The first step occurs with a reduced rate of decline in the ozone. The second step reflects not only a reduced rate of decline, but a leveling off of depletion altogether. The third step comes with a substantial ozone increase that can be linked to decreases in halocarbons. This process is referred to as healing, which is the chemically driven increase in ozone. Over time, it has been observed that the ozone hole opens in August and reaches its maximum size in October. As the ozone heals, the hole observed in early September is growing smaller and opening at a slower pace. Since 2000, the Antarctic ozone has healed the most in the month of September. Additionally, the hole size in October is expected to decrease in the 21st century when chemical destruction begins to slow. As ozone-depleting substances continue to reduce, the ozone will continue to heal.
The size of the Antarctic ozone hole has been decreasing over time since 2000, with the exception of a period of time in the year 2015. The largest size of the ozone hole was recorded in October of this year, but researchers have suggested that this increase in size was due to geophysical events on the Earth's surface, such as volcanic eruptions, changes in temperature, and other environmental dynamics. In particular, this 2015 increase is believed to have occurred due to the Calbuco eruption. After accounting for factors including dynamics, temperature, and volcanic factors, the results of this study illustrate the emergence of healing of the Antarctic ozone. The results combine together the trends of balloon and satellite data, volcanic aerosol measurements, and the chemistry climate models to model the progressive recovery of the ozone after the implementation of the Montreal Protocol.
This experiment relates to Biology 1510 because increased ultraviolet radiation can slow down photosynthesis in primary producers. Looking at the food chain from a bottom-up perspective, decrease of primary producers would cause a decrease of all of the higher trophic levels. This article is relevant to society because the hole in the ozone can have a detrimental effect on human life. The reduction of primary producers' ability to perform photosynthesis can deplete the human food supply and affect the amount of oxygen in the atmosphere, as well as cause harmful health consequences in humans.